started the recording. I welcome back all the participants for the second session. It's my privilege to welcome today's session handled by Dr. Arun Rajkumar on responsible AI as a part of our FDP on responsible AI. It's a privilege to have you with us today, sir. And we are excited to learn from your expertise in this vital and rapidly evolving field. Dr. Arun Rajkumar is working in the Department of Data Science and AI at IIT Madras. Prior to joining IIT Madras, he was working as a research scientist at Concordant Labs, which was earlier called as Xerox Research Center, at Bangalore for 3 years. He earned his PhD from Indian Institute of Science, where he worked on ranking from pairwise comparisons. He was awarded the Young Faculty Recognition Award for the year 2022. Adding to it, it gives me immense pleasure in welcoming our alumni, Dr. Arun Rajkumar, who graduated from the Department of Computer Science and Engineering at PSG College of Technology. Your work in AI and its ethical implications has made a significant impact, and we are eager to hear your insights on how we can shape AI technologies in a responsible and sustainable way. We look forward to an engaging and thought-provoking session. We are sure that your knowledge will inspire and enlighten all of us. Over to you, sir.
Thank you, Dr. Surya, for the. I hope I am still audible, and if there is an issue, just let me know. So great to be here. And what I wanted to discuss today in today's session in this FDP is privacy matters with respect to machine learning and AI. So just to get a feel for the audience here. So I'm sure all of you understand standard techniques in machine learning, or at least have a broad idea of what machine learning is. Is that fair enough to say? If I don't know if you can, yeah, you can, right? So yeah, thanks, Dr. Meena, for the response. So so let me do a brief introduction here. So okay. So I hope you're able to see what I'm writing as well, right? So yeah. So what is standard machine learning? So at a very high level, standard machine learning is the following, right? So I have some data, and then I feed it to some algorithm, which is a machine learning algorithm. Maybe the data is, you have a bunch of emails. Some of the emails are labeled as spam. Some of the emails are labeled as not spam. And then there is some algorithm which is going to take this data, and then it's going to output what we are going to call as a model. And this model is now going to tell us, for a new data point, let's say a new email, whether this email is a spam email or a not spam email, right? So this is the standard binary classification problem that all of you might be familiar with. This is the very, sorry, is somebody speaking? I'm kind of getting some disturbance.
I'll check it, sir.
Yeah. Maybe there is some user called iPhone, if they can mute. Yeah, thanks. Yeah.
I'm muted, sir. I'm muted.
Thank you. Yeah. So this is the standard machine learning model, right? So you have some data, and then there is some algorithm, and then the algorithm is going to produce some model. And now we know of so many different algorithms. I mean, you have the deep learnings of the world today, and even the standard classic algorithms like support vector machines, logistic regression, naive Bayes, whatever it is, right? So you might have a lot of algorithms that from machine learning courses that you may have taken or have read about. And what these algorithms do is they make sure that the model is as accurate as possible for the test data, right? So that is the data that comes later, for which you don't know the labels. You hope that the model is doing well. Now, all this is fine, right? So in the classical machine learning sense, that's all you care about, right? So you had data, and the algorithm is giving you a model, and the model is working really well on test data, and everybody is happy. But what might happen is the following, right? So what would happen is, now there might be, an adversary, somebody who is trying to, kind of break our system, who might have access to this model, right? So by which I mean that, let's say if you have a neural network, then by model I mean all the parameter values of this neural network. Somehow, this model, let's say I'm giving it out to the world, and now it is for public to use this model to make prediction. And let's say there is somebody who is adversarial who has access to this model. Now, the question that we want to ask is, in case if our data is private data, right? So, or what I can call as confidential data. For instance, it may not be email data. It might be, let's say, healthcare data. And then the problem that you are trying to solve is, given your health details, whether you have a certain disease or not, right? Now, your health details might be very, very confidential. And now we have this algorithm, great algorithm that produces a model, and this model is given to an adversary. Adversary has this model. Now, the question is, can the adversary, using this model, can the adversary recover some information about the data? If the adversary is able to do that, then you have provided your health-related information to the modeler, who is taking your data, let's say the hospital, and then running this machine learning algorithm and produces a classifier and gives the classifier to the adversary. Now the adversary has the classifier in his or her hand. Now, using that classifier, if the adversary is able to figure out something about whether you have a particular disease or not, then that means there is a breach of privacy. Now, this is a very important thing because, though you are not revealing your healthcare data exactly, can it be indirectly revealed potentially using the model? And if that happens, so now me as a patient is going to be very, very, I'm not going to be very happy in giving my information to be used by the hospital to produce classifiers. But producing these classifiers has immense social benefits because, not all hospitals have millions of, let's say, patients. There might be a new hospital that is coming up where the doctors might really benefit from using such a model to make predictions for, whether for the patients in their hospital. So it's a socially good thing. But at the same time, it is important that we preserve the privacy of the data, even if the model is revealed to an adversary. So the bigger question in privacy in AI is, how can we develop algorithms such that, you can make these patients confident in giving their data to the algorithm without, any thoughts about their information being revealed to somebody who is an adversary, right? So this is the question that we want to kind of tackle. And, eventually in the next 1.5 hours, we'll try to see, what are some simple methods that can be used to do this. But before I start discussing those methods and then we'll set some context and so on, I want to know your thoughts, right? So what do you think? How do you think this is an important problem? And if so, what are some thoughts as to how you would go about thinking about this problem? Any thoughts from the audience? Is the problem clear, or if there are any questions about the problem, you can let me know as well. Anybody in the audience?
Participants, feel free to express your thoughts. Either unmute yourself or you can post it in the chat window.
Yeah. Anybody? Any thoughts? Right. So I think I think let's make it as interactive as possible so that we get benefited from these sessions. Yeah. Anyone? Any thoughts? I mean, is the problem clear to everybody? Is there any?
Yeah, sir, it's clear.
Okay. Okay. So now, how do you think you will solve this problem? What are some thoughts? Let's say what's one machine learning algorithm that you know about, if you can
So how to ensure the trust of this trust level of the systems?
Correct. So that's the question, right? So we want to make sure that the systems are trustworthy. That's the main question that we are trying to answer. And the question is, how can we make sure that, me as a participant in this machine learning algorithm, by giving my data, I'm sure that, there is nobody out there who can figure out my information. That's what we want to find out. So that's the question that we want to answer. But before, it might not be immediately obvious how to do this. It's not a straightforward thing, but we will get there by end of this talk. I'll try to argue why there's a simple method where you can potentially preserve privacy. To set context, to get there, what I'm going to do is we are going to kind of slightly look at a different problem and ask the same question. And then see, this is a simpler problem maybe, and then we can see if there is a way to make, use ideas that we'll develop in the simple problem, then to apply to the machine learning context that we have. So the problem is the following. Let's say let's say this is election time, and you want to know how many. What is the average number of people, or the number of people who voted in a particular city? Let's say Coimbatore, right? So in Coimbatore, let's say Pyramid is where PSG Tech College is, and that's like a smaller locality. And then we want to know, as somebody who's surveying people in this area, you want to know how many people voted in Pyramid in the previous election, right? So let's say there are 1,000 people, right? So that's the number of people in Pyramid. That's definitely not the number, but let's say for our purposes, let's say there are 1,000 people, and then we are going to call these people x1, x2 till x,000, right? So there are 1,000 people. The first person is x1, last person is x,000. Now, what are these values, x values? Well, these values indicate whether that person voted or did not vote, right? So that's the thing. So for instance, x1 could be 1, which means that the first person voted. x2 can be 0, which means that the second person did not vote in the election. x,000 might be 1, which means that person voted. Now you want to know how many people voted in Pyramid, which means, what do you want to know? You want to know as a surveyor, you want to know x1 plus x2 plus ... plus x,000. Right. So what does this sum give me?
Total number of candidates to be voted.
Yeah. So total number of people who voted in the previous election. That's what this value will give me. Now, if I ask 1,000 people, and if I told me truthfully whether they voted or not, then I can just add up all their values and I know how many people voted in Pyramid. Problem is solved. But let's say voting or not voting is a very confidential thing, right? So I don't want to really reveal whether I voted or not. So because there is a taboo attached. If you don't vote, then you have not performed your democratic duty or whatever it is. Somehow I'm not very comfortable in revealing my answer, right? So truthfully, but I am a socially responsible person, which means that I want you to figure out how many people voted or not. That is something that I really want you to figure out. Which means that if everybody actually told the correct answer, then you will be able to figure out. But there is this problem that I don't want to give you the answer also, because that will reveal my information. Though I'm socially minded, I don't want to reveal the information also. Now there is a big confusion here, right? So on the one hand, I want to preserve my privacy, which means that I don't want to give you the information whether I voted or not. On the other hand, I want you to get a reasonable idea about how many people voted in Pyramid. Now, how do you think we can solve this problem? Can we devise a mechanism where I'll at least get a reasonable idea of how many people voted in Pyramid or not? How do you think we can solve this problem?
Sir, we can use supervised learning.
Okay, and
Hello, sir, I am audible.
yeah, you're audible. Yes, go ahead.
Whether we can use supervised learning, sir?
How would you
How
use?
how many of them are voted or not voted like that?
So problem is not even machine learning at this point, right? So basically, let's say forget pyramid. Let's say that how many there are 111 participants, 139 participants in this call, right? So I'm going to ask each one of you whether you voted or not, and you either say 0 or 1, and then I will sum it up. And then let's say if 60 people voted, then there will be 60 ones, and the remaining will be 0. I'll sum it up and I'll get the answer. But
Yes,
you don't want to reveal that information to me. But you want me to get a good. You still, all of you want me to get a good enough, rough value for the sum, but you don't want to give me the actual value, right? So that's the confusion here, right? So you want your information, you want to reveal information, but then you don't want to reveal information also, right? So
Actually, sir, actually, first there is a concept of intent analysis. So before, first we have to understand the intention, context, in which context the answer is required. So because the person who already given the vote or in middleman who is going to analyze.
so
that is important.
Let's say in this case, all of you, all the 139 people in this room are somehow your intent. You know that my intention is to understand. I'm doing just a survey, right? So and you know that my intention is not bad, right? So all of you know that my intention is just to get the number of votes that in the room, but you have some problem with revealing your actual answer because you don't want me to know what is the exact value that you gave me, right? So that's the problem. Now, if you don't care about whether I am getting the correct vote or not, right? So getting the correct count or not, what can you do?
Sir, we need
So
to
in
train
that
the
case-
model by giving previous data sets.
No, there is
Previous year data sets.
right? So I'm saying let's do it now, right now here, right? So there's no previous data set. There's not a machine learning problem, right? So I'm going to ask all of you, give me, give me whether information whether you voted or not. Right?
Some kind of declaration or oath kind of things we can put some provision.
Sir, we can put some sensors like that, whether they voted, if they, by using sensor, they can voted or not, like that.
No, I'm asking now, madam. So I'm saying now, right now in this Zoom call, let's say I want to figure out how many of you voted in the previous election, right? So I'm saying, I'm asking all of you to type in the, let's say the chat box, 1 or 0, telling me whether you voted or not. Now that is information that I'm able to see, right? So, but then this is you want to keep this information private, right? So if you want to keep this information private, what can you do?
Sir, can I answer, sir?
Yeah, please go ahead.
Don't care category to be added with in voted condition also, non-voted conditions also.
Sorry, madam, I didn't understand. Say that again.
Don't care category. So whoever not willing to give the information, that information to be added to in voted category and also non-voted category. So that constraint we want to add.
Okay, so you're changing the way the setup should be. I'm saying let's not change the way the setup should be. You have to give me either a 1 or 0, right? Now
by checking the age of the people.
There is no other information, madam. So I don't know your age now, right? So this is in this Zoom call, I want to do this, right? So I want all of you to give me 1 or 0. Now, if you don't care about whether I will be able to compute the sum correctly, then what can you do? Well, what can you do? You can lie.
Sir, right? Whether we can encrypt the messages that we have given.
That's a good point, right? So you can encrypt and do certain things, but the problem with using encryption to preserve privacy is it's a very computationally hard thing, right?
Yes, sir.
So what we are going to, that's a good point. So let me make one comment about that. What we are going to use here, discuss today is not cryptographic privacy.
Okay, okay, sir.
The usual thing that comes to mind when we talk about privacy is cryptography. You do encryption and decryption, and then somehow in a private way you can transfer that information. But that's typically very expensive, and especially when you want to, let's say you think of ChatGPT, which has 100 billion parameters, right? So now if you want to encrypt those parameters and give you, that's simply going to be humongous, right? So let's not worry about doing encryption at all, right? So what we are going to do, let me give you an answer. What we are going to do here is we are going to use a statistical notion of privacy, and it will become clear what I mean by that as we go along. So now the way it's going to happen is as follows, right? So now you have a 1 or 0, which is your truthful information. Now what you can do is, if I ask you, hey, did you vote or not? You can do the following. You can pick a 1 rupee coin from your pocket, toss it. If it falls heads, you will say I voted. If it falls tails, you will say I did not vote. That is, if it falls heads, you will give the answer as 1. If it falls tails, you will give the answer as 0. Now, what will happen if each one of you did this? What will it preserve privacy about your truth?
So we will consider the possibilities of head and tail, no, sir.
We'll consider what?
Possibilities.
What possibilities?
The head and tail, you say, no, we want to consider the possibilities, no, sir.
Yeah. So the method that you are going to use, each one of you is going to use, is the following, right? So let's say you voted, right? So which means that you should actually give me 1. But what you are doing is you are just tossing a coin. If the coin falls heads, you will tell me 1. Otherwise, you will tell me 0. Now, each one of you is doing this. Now, I have some information that I collect in this method. Now, what is the problem with this method? Does it preserve privacy about your data?
Yes, it preserves privacy, sir.
Very good. It preserves privacy because I have no clue whether you voted or not, because you are giving me a completely random response, right? So you are just tossing a coin and giving me a response. So have we solved the problem? So have we solved the privacy problem? But what is the issue then? Yes, we have solved the privacy problem.
Yeah, privacy problem was solved, but the person might have voted, but it might have given instead of head, it has given another side.
Very good, right? So what has happened is you have solved the privacy problem, but the problem that you have not solved is the data that you are giving me is completely useless. Now, if I just sum up the x1 plus x2 till x1000 or x139, if there are 142 in this participants in this room, I'm going to get some number, maybe 70 or some number I will get. That number is simply useless. It has no relation to the actual truth. Maybe only 10 of you voted, but then I might get a number which is 70, right? So which means that if you just toss a coin and then give me the answer, privacy is preserved. But the utility of the final answer that I am going to get using your data is simply 0. There is no utility at all. So now, that is one extreme. The other extreme is you tell me the truth. If you tell me the truth, my utility is 100%, right? So because I have got truthful data, I can actually do the summation and I know exactly how many people voted. But there is no privacy because I know each one of you whether you voted or not. So on the one hand, you can just randomly give me an answer, toss a coin, preserve privacy, 0 utility. On the other hand, you can be truthful, preserve utility, but then 0 privacy. Both are bad. Now, how can we balance this? What then should we do? Any idea? Is the privacy utility part clear to everybody?
Yes, sir. Yes, sir.
Okay, great. Okay, so now I'm now requesting all of you to think and tell me, how can we kind of, be somewhere in between, right? So we don't want 0 privacy, 100% utility, or 0 utility, 100% privacy. We want to be somewhere in between. What can we do?
So shall we add some noise on the true data?
Okay, so the true data is either 0 or 1. That's a good thought process. Let's think a bit more about that, right? So what do you mean by adding noise? So the true data is either 0 or 1, whether you voted or not voted, right? And now you have to give me whether 0 or 1, right? So which means what is your notion of noise?
Some random
Give
value,
incorrect.
adding some random value onto there.
But if you add a random value, then you're not going to get a value between 0 and, I mean, you might
We
get.
have to give a correct value, but with some policies.
What do you mean by policy?
Policy like have to make some rule ethics and all.
Okay, so you're almost there, right? So yeah, so follow some distribution by considering sample population. We don't know anything, right? So we don't know anything sample population. I'm just trying to do it here in the Zoom call, right? So I'm just asking you all the information. So let's. I think Dr. Soni Sweta had a point. I'm just going to think a bit more about that, right? So let's think of it this way, right? So there is a truth value which is x1 ... xn. Okay, so there are, if n means there are number of people, so each of the xi is a value which is either 0 or 1, right? So the truth is either 0 or 1. Now what am I going to reveal to the surveyor? Well, I'm going to reveal revealed value. The revealed value, let me call it y1 to yn. Okay, so where yi is also 0 or 1, right? So which means that, for example, x1 is the truth, maybe the first person voted, right? So which means that x1 is 1, but then the first person is going to give me y1. Y1 is also some value between 0 and 1. Now there should be some connection between y1 and x1, which we will establish in a minute. Similarly, yn is connected to xn, y2 is connected to x2, and so on and so forth. Now, how is the revealed value connected to the truth? Well, it is connected as follows, right? Yi, that is what the ith person says, let's say, is xi, which means that the ith person is saying the truth, right? So which means that is saying the truth, but then he's not saying the truth always. He's saying the truth with probability, let's say 0.8. And he will say 1 minus xi, which is the false answer with probability 0.2. Right? So what does that mean? That means that I have a value which is 1 or 0. Let's say it is 1. That is my xi. Right? So I am the ith person. My xi is 1. Now I need to give you 1 or 0. I'm going to be truthful 80% of the time, which means that I'm going to toss a coin which falls heads with probability 80%, 0.8, and which falls tails with probability 0.2, which means that the coin, let's say, is heavier on one side, which means that there is more chance it falls on heads. How much chance? Let's say 0.8. Right? So 80% of the time it will fall heads. So now I'll toss that coin. If that coin falls heads, then I will reveal the truth. If that coin falls tails, then I will lie. Right? So now everybody, let's say, is doing this. Now, if this probability was 0.5, then I will lie with, I'll say the truth with probability 0.5 and lie with probability 0.5, which means that I'm basically giving you some random answer. That the actual truth does not matter at all, right? So, but if it is probability is 0.8 instead of 0.5, then most of the people are going to give me truth values. Because for most of the people, when they toss the coin, it would have fallen heads. If there are 142 people in this room, 140 people, all of you are tossing coins, and for each of your coin, the chance of falling heads is 80%, then roughly 80% of the people would tell me the truth. 20% will tell me the lies. I don't know who told the truth, who told the lies, which means that if you ask specifically, maybe, Dr. Surya, did she tell me the truth or false? Did she lie? I don't know. but still I know 80% of the people in this room gave me the truth value. So which means if I just sum up the values of everything that you are giving me, now it may not be the exact number of people who voted in this room, but it is reasonably okay, right? So what we have managed to achieve is a trade-off between privacy and utility. If I toss a coin with probability half and give you the answer, then I'm completely private, but it's useless. But now I'm tossing a coin which is more true than false. So which means that helps me preserve something about the privacy. Yeah. So that is the basic idea. Now the question is, how to choose this 0.8? Can it be 0.8? Can it be 0.9? Can it be 0.7? How do you choose this number? I'm going to talk about that next. But before that, let me pause and ask if there are any questions so far. Is this clear?
Participants, kindly be interactive.
Instead of probability, because all these are the concept of human mind and decision making and all. So if we are using the fuzzy mathematics, so I think it could be better as per the probability, because it is only mathematics we deal with the some belongingness with the positivity and negativity. And say person maybe assume as 0.8% positive belongingness and 0.2% negative. Means at a time I can prove a person can be voted and its belongingness is 0.8 and is not voted with the probability with the belongingness of 0.2. So I think fuzzy mathematics is better than the probability. Is it okay? Correct?
In this, see, so
in context of human mind, because they are always think like fudgy, vagueness. The answer is vague.
Probability is trying to achieve something similar, right? So what we are not allowed is numbers between 0 and 1, right? So you cannot tell me 0.8 as an answer. Then you are revealing something about your fuzziness, right? So if you tell me 0.8, then it means that I know most likely you voted. I can perhaps figure that out, right? So we want to avoid that. So you are always going to give me either 0 or 1. All I'm saying is you are going to give that in a probabilistic. That's right. So this is one method, right? So I'm saying maybe there is a fuzzy way to do this, but I mean I'm not really going to prove the theoretical aspects of this in this FDP. But what we can argue is that this method, when we'll generalize it in a bit, kind of has a nice privacy utility trade-off. What do I mean by that? I mean the following, right? So in practice, what this method, let me give this method a name. This method is what is called as a randomized response. This has been known for, I think at least 20-30 years, especially in the surveying literature. That's where this idea started. What you do is, in fact, you don't, this 0.8 and 0.2 is something that's a flexible parameter. What you do is you reveal the truth with probability. WP is with probability. And I'll write this and then explain what it is. E power epsilon divided by 1 plus e power epsilon. This is the truth. This is the chance with which you tell the truth. And 1 minus xi is the chance with which and you're going to say 1 minus xi with probability 1 divided by 1 plus e power epsilon. This is the lying probability. Now, this epsilon is what is called as the privacy parameter. It's the privacy parameter. That is something that we can set based on how we want to balance this privacy utility trade-off. Now, if epsilon is 0, then what do you think happens? What is the value? What is the probability? What is this value if epsilon is 0?
1.
Everything will be 0, I think.
1.
Why is it 1?
E power 0, 1.
Yeah, e power 0 is 1, but this is e power epsilon divided by 1 plus e power epsilon.
1 by 1.
So 1 by 1, 1.
Is it 1 by 1?
1 by 2.
1 by 2, sorry, 0.5, sorry, sir. 1 by 2.
Right? So if epsilon is 0, this is same as saying I'm setting this value to be 0.5, which is like our completely random response, right? So I'm just going to toss a coin and then give you, which means that if epsilon is 0, then it is completely private. That's what this means. But if epsilon is larger, the larger epsilon becomes, the more closer this e power epsilon play 1 plus e power epsilon gets closer and closer to 1, and you are revealing the truth with larger and larger chance, right? So now the question is, okay, so this can control how private I want it to be, but can this also tell me information about how good is the final answer that I will compute, right? So now you want certain level of privacy, so all of you will choose an epsilon, and let's say that, and then toss a coin with probability e power epsilon by 1 plus e power epsilon, and then give me whether the truth or the lie, right? So now I have got all the information, and let's say I'm trying to do the average, right? So I will compute an average or sum or average, anything is okay. I'm going to compute that, and now I'm going to ask, how good is this, right? So how good is the utility of this method, right? So this is what is called as the randomized response. First, how good is the privacy? Let's ask two questions. How good is the privacy, and how good is the utility? So what we have done so far is we have figured out one way to give information to me. And the way is that we'll first fix an epsilon. And once the epsilon is fixed, when I ask you, hey, did you vote or not? You're going to take a coin whose probability of coming up heads is e power epsilon divided by 1 plus e power epsilon. And then you will toss that coin. If it falls heads, then you will tell me the truth. Otherwise, you will lie. Right? So this is our protocol. Each one of you will do that and then give me the answer. And then I will do the average of this. And then I will know the average number of people who voted in this Zoom call. Let's say that is our setup. Now we are going to ask how private is this method and how much utility does this method have? These two questions we'll try to answer. Now let me tell you how private this method is. The first thing. Now this method has a certain very interesting privacy guarantee, and the guarantee is as follows. Now, if you take two sets of people, right? So let's say consider two data sets. Let's say x1 till x100, 100 people in this room, right? So each one has your truth value, and then there is a different Zoom call where 99 people are present. All your or let me say it this way, right? So let's say except one person, everybody else is the same, right? So this is data set, let's say D, and this is a data set D prime, which is exactly same as data set D, except that the last value is different. The only thing that is changing is the 100th value. So I should say 100. X99 and X100 is different. So these two are different. The first 99 people are the same. The 100th person is, if this person has a 1 value as truth, this person will have a 0 value, right? So only one value changes. Now we want to know, if let's say these are two different Zoom calls, and in the first Zoom call, these 100 people are present with certain truth values, and in the second Zoom call, these 100 people are present, but 99 people have the same truth values. Just one person has a different truth values. Now I'm going to ask, give me whether you voted or not to these 100% in the first Zoom call. They are going to give me y1 till y100 following the protocol, tossing the coin, etc., etc. The same thing I do for this Zoom call also. Now they will give me y1 prime till y100 prime, right? So they will also follow this. Now what I am going to do is, I am going to ask the question, when will these two answers be the same, right? So in other words, the data set changes in only one entry. Now there is a randomized response that I'm getting from two data sets which differ in only one entry. Now let's say, okay, let's make it even simpler. Let's say this data set was 1, 1, 0, 1, 0. Let's say there are only 5 people. Now this data set is 1, 1, 0, 1, 1. This is the truth. Now I toss a coin and then I get some, I get some answer. And let's say that answer is 1, 0, 1, 0, 0. Right? So this is what is the answer that I have from 5 people. Now let's say an adversary gets hold of these answers, right? So 1, 0, 1, 0, 1, right? So 1, 0, 1, 0, 0. Now the adversary has this information, Now in addition, let's say the adversary knows the truth about these 4 guys, right? So there are 5 people. This is person 1 whose value is 1, person 2's value is 1, person 3's value is 0, person 4's value is 1, person 5's value is, let's say you are person 5. In this situation, your value is 0. In this situation, your value is 1. Now here is an adversary who observes the randomized response and then also knows the truth value of the first 4 people. Somehow he has gotten hold of the true value of first 4 people. The only thing that the adversary does not know is whether you have a 0 or a 1. This information is the only thing that the adversary doesn't know, right? So now by looking at 1, 0, 1, 0, 0, if the adversary can figure out whether you have a 0 or 1, then the adversary has broken the privacy. Now the question is, by looking at this randomized response, will the adversary be able to say whether this data set generated this response or this data set generated this response? Even if the adversary knows these 4 values, can the adversary figure out which of these data sets generated this response? If we ask that question, in other words, the chance that each of these data sets could have generated this response with certain probability, because it's a probabilistic mechanism, right? So maybe there is some chance that this data set generates this response. There is some chance that this data set generates this response. Now, what you can prove is the following, right? So the probability that first data set generates 1, 0, 1, 0, 0 divided by the probability second data set generates 1, 0, 1, 0, 0 is at most e power epsilon. Let's meditate on this statement for a bit, right? So what is this telling me is something very crucial, very important, right? So if the randomized response was performed and the adversary got hold of the random answers 1, 0, 1, 0, 0, let's say I was adversarial, right? So I'm trying to figure out, whether you had a 0 or 1. If I know, let's say I want to figure out whether Dr. Surya has a 0 or 1. I know the truth value of everybody else. I just don't know the truth value of Dr. Surya. Now I'm asking all of you to give me the truth value, but then you are flipping these coins and giving me the answer. The answer that you have given me is 1, 0, 1, 0, 0. From this, I want to backtrack and figure out whether Dr. Surya has a 0 or 1. Now, what I'm saying is that now the chance that, Dr. Surya having 0 generating this response 1, 0, 1, 0, 0 divided by Dr. Surya having 1 and all of you having the same answer generating this response 1, 0, 1, 0, 0 is not too far away. which means that both of these data sets, whether Dr. Surya has 0 or Dr. Surya has 1, the chance that I am observing 10100 is almost the same, which means that I will not be able to figure out with very high chance, with very high probability, whether Dr. Surya has 1 or 0, right? So which means that, the ratio, right? So the clarity that I'm getting, whether the information that I have 10100, did it come from a data set where Dr. Surya said 1 versus did it come from a data set where Dr. Surya said 0? That ratio is, very small. It's e to the epsilon, right? So if I can control this ratio by controlling epsilon, right? So which means that if epsilon is small, then it means that, I have confused enough that I won't be able to figure out whether an individual is saying 1 or 0, right? So I can only get it up to e power epsilon, right? So that's my, leeway, but that's a very small number, right? So which means that I won't be really able to say whether specifically a single person had a 1 or 0. So that's the broad idea, right? So now, this method of preserving privacy is what is called as an epsilon privacy in randomized response. We will see how this is useful in machine learning in a bit. So this is privacy, right? So this is the sense in which we are going to say something is private. In what sense? Well, if I just observe the outcome, I won't be able to know whether a specific individual said 1 or 0. No matter the individual said 1 or 0, the chance of observing this specific outcome that I have in hand is the same. It's not the same, it's more or less the same. It's very close to each other, right? So that's this ratio. Right, so this ratio is almost close to 1, right? So e power epsilon is like 1 plus epsilon, right? So it's roughly 1 plus epsilon, which means that this is almost close to 1, which means that these two values are almost the same, which means that I won't be able to figure out whether it was 1 or 0 for a specific individual, which means that individual now is happy that, well, I am able to give my data because, because of this entire randomness that is happening, the adversary, even if the adversary knows everybody else's data, the adversary still will not be able to figure out whether I gave a 0 or 1. The adversary is still going to be confused. The random procedure is going to confuse the adversary, and the adversary will not be able to know whether I gave a 1 or 0. Right? So that's the notion in which that's the definition of privacy that we will have. Is that at a high level clear? Even if you did not understand the probability aspects of it, is at least the idea that, by just looking at the random outcome, I won't be able to figure out whether a specific person had a 1 or 0 with very high probability. That's the basic idea that we are trying to argue here. Is that roughly clear to everybody?
Yes, sir.
Okay, great. So now let me also quickly talk about the utility aspect of this, right? So the utility is, how good is this, right? So if you make it very, very private, yes, it is private, but then how useful it is. Again, it takes some work to prove this, but I won't do that. So utility, I'll tell you what the utility is, and then I'll talk about, what I mean by that, right? So this is a random process, right? So which means that, I ask you for the truth, you are giving me random values, which means that if I get all the values and then I compute the average, that's also going to be some kind of a random quantity. Now I'm asking, how good is this random quantity that I have with respect to the truth that I would have had if all of you responded truthfully? If all of you gave me the actual answers, I can compute some average value. But now I am computing some random value because you are giving me some random values. So now what is the difference between these two, right? So which means that, let's say I have, sum over I equals 1 to n xi, which is the truth, right? So this is the true value that I want to compute. Maybe if I wanted to average, I can do 1 by n of this, right? So this is the true average number of people who voted in this room. Now, what I'm actually computing is, let's say, sum over I equals 1 to n yi, which is not the truth, but then the actual thing that you reveal to me, which is, by tossing this coin, you kind of confuse the truth and then you are giving to me. So this is what this can be computed by can be computed by me. And now I want to ask, how close are these guys? So if I subtract this, how close are these? Smaller this value is, the closer the truth and what I am computing is, which means that the utility is higher. Is that clear? Because this is the actual truth that I would have gotten had all of you been, truthful. But this is what I'm actually able to compute, because you randomized and then gave me random responses. And now I want to ask, how good is the randomized average compared to the truth? And now one can argue that this difference grows as follows, right? So this, with a very high probability, this grows something like 1 by epsilon square root of n. This is in order notation, 1 by epsilon square root of n. Let me explain what that means. This means we fixed a privacy parameter, epsilon. Let's say epsilon was some number, and that translated to some probability with which you will flip the coin and give me the truth. That was our mechanism. That epsilon is fixed. Once that epsilon is fixed, then we know that in terms of privacy, I have this epsilon privacy for the randomized response. Now, how good is this? I'm now asking a question about utility, and then the utility that I am getting is the difference between the truth and what I exactly end up computing, and that is something like 1 by epsilon square root of n. Now, what does this mean? So when will this value be small, right? So I want this value to be small. Why do I want this value to be small? Only then the truth and what I am computing will be close to each other. If this value is 0, then that means that the truth is exactly same as what I have computed, but I'll never be able to get 0. But what I can get is by setting epsilon, and where n is the number of people I'm asking this survey about, I'm getting something like 1 by square root of n into epsilon, which means when will this be small? If epsilon is small or large? When will this value be small?
Epsilon is large.
Yeah, if the larger epsilon becomes, right, so the smaller this value becomes, right? But the larger epsilon becomes, now if you look at the privacy, this value becomes larger. The larger this value becomes, the larger e power epsilon becomes. So I'm going to reveal the truth with the larger and larger probability. Right? So e power epsilon divided by 1 plus epsilon will get closer and closer to 1 as epsilon becomes larger and larger. Which means that if I really want this value to be close to, this difference to be close to 0, which means I want high utility, then epsilon should be large. But if epsilon becomes large, my privacy becomes smaller, right? So because I'm revealing the truth with more and more chance, I'm kind of, losing out on privacy. On the other hand, if epsilon is small, then this difference is large, which means that what I'm really computing and what is the actual truth are far apart. The difference is large, right? So I lose out on utility. So on the other hand, I will gain in privacy. So epsilon is one number, single number that kind of tells me how is the privacy utility trade-off, right? Smaller the epsilon, higher the privacy, lower the utility. Larger the epsilon, higher the utility, but lower the privacy. So now as a designer, it's completely up to me to convince the, to people to give me the data by saying that, hey, this is the amount of privacy that we can guarantee. Will you be able to give your data to this algorithm or not? Right? So, and we can make a very, very strong statistical claim there, right? So by saying, this is a very statistically sound way to say, I can guarantee that you will have, 99% privacy or 95% privacy. The chance that your data will be revealed is very, very small, right? So there is always a chance it can be revealed, but it's going to be very, very small. And now, are you willing to give your data to me? I can make such statements now to the public, right? So, and then, if the chance is 99.99%, maybe I'm okay to reveal my healthcare data, right? So because there's a very less chance that somebody is going to be able to backtrack and figure out. So that's the notion of privacy versus utility trade-off that we'll talk about in a method called randomized response. We'll talk about the machine learning equivalent of it next quickly, but this is the overall idea, right? So the single number kind of balances privacy and utility. So let me pause here for a second and ask if there are any questions so far. I know if you have not seen probabilities for a long time, this might all sound new, but then the basic idea is very simple. You're not revealing the answer, but then you're revealing a noisy version of the answer. But that noise is in flipping the truth. With some chance you will say the truth, with some other chance you will not say the truth. And if the chance is correctly manipulated, then that is the epsilon parameter that manipulates with what chance you are saying the truth. And then there is that chance will also lead to how good is your answer, which is the utility. That's the trade-off that we can match. So let me pause here. Any questions or any thoughts so far?
Sir?
Yeah.
Here you are dealing with the only data privacy. So any other use case can you say where we can use this kind of thing, this mathematics in research, where we can use?
So so this method is used for privacy. This is not even in machine learning yet, right? So what?
Yeah, only in the data privacy or?
Yeah. So this is this method is used for data privacy, but the tools to analyze these probability and things like that are ubiquitous, right? So their applications, whole of machine learning builds on probability, right? So in terms of how confident are you about your prediction, etc., etc. So tools of probability are being used here, but this specific method is only used for privacy. Yeah.
Yes, sir. So we need to set the value of epsilon between 0 to 1. So
not 0 to 1, right? So between it can be any value, any positive value, right?
Okay.
Yeah. So
but there is a trade-off between that utility and that actual that false data.
Correct.
So how to fix this value? Is there any metric to check whether the epsilon value created is correct or not? Because currently I'm working on that federated learning with the differential privacy preservation.
Yeah.
So when the data is collected at the global head, the accuracy is less.
Yeah. So we'll talk about differential privacy in a minute. That's what I was coming to. Okay. So this is a flexible parameter. Now, depending on your application, certain epsilon may be enough for, certain levels of privacy may be enough in certain applications. More privacy may be needed in certain other applications. Now, the fundamental thing is, if you are gaining in privacy, you have to lose in utility. If you're gaining in utility, you have to lose in privacy. Now, it's completely domain specific. How is the domain asking you to be more private or less private will determine whether epsilon should be large or small, right? So there is no recommendation that I can give, but in healthcare it might be different, in finance it might be different, in emails, if you want to preserve privacy of emails, maybe it's lesser. You are okay with 90% privacy, but then in healthcare maybe you need 99% privacy. If it's your financial data, maybe you need 95% privacy. That's completely domain specific. But what this is giving you is a flexible way to figure out, once your domain tells you, hey, this is the amount of privacy you need, then you can backtrack and work the value of epsilon.
But lesser the epsilon reduces the accuracy. Am I correct?
So lesser the correct, which means because lesser the epsilon, this is a small value, so this is a large value. If this is large, this difference is large. This absolute difference is large, which means that what I am computing might be, the truth might be 0.7, but then I might be computing 0.1, right? So this difference becomes larger.
Okay, sir.
Yeah.
So to adjust the epsilon value, can we use accuracy to adjust the epsilon value based on that accuracy of that model? Can we adjust the epsilon value or?
So this is at this point there is no machine learning or model yet, right? So this is just I'm just doing averaging, right? So now we will see for machine learning models. The next thing that I'm quickly going to talk about is how does this translate to machine learning models, where different models will force you to use certain amounts of epsilon in a different way. I'll talk about that in a minute. Yeah.
Okay, sir. Thank you. Thank you. Thank you.
Sure. Yeah. So let me talk about the machine learning use case for this. So the machine learning use case is slightly different. What I would like to call it as, trusted curator model. So here the difference is slight but very important. So in the method that we have seen so far, or in the setting that we have seen so far, each one of you had a number which is either 0 or 1. But and you had to give that number to me, and I had to compute the average. But you did not trust me, right? And that's the whole reason why you had to flip coins and then give me a randomized response, because you did not have trust in me. Because I could have gotten your answer, computed the average, and then somehow figured out who has what number, right? So because you're giving, if you gave me the truth, I mean, even without computing the average, if you give me the truth, I know what your answer is. Because you did not trust me, you are giving me a random response. Now, in a trusted curator model, it's slightly different, which is typically what the machine learning model is, right? So let's say I am now a hospital. Now you are going to give me your healthcare information. Now it's not that you are not trusting me. You trust me, right? So you are okay to give me your data to me. But what you don't trust is, if I compute the average from all your data, and now if I release the average to the outer world, now the outer world is whom we don't trust, right? So there might be an adversary sitting outside who has access to this average. Let's say I get zeros and ones from you. All of you trusted me. You gave me the answer. I computed the average. I gave the average out to the world. Now, if there is an adversary there who again knows everybody's answer except Dr. Surya's answer, and now also knows the average, then it's just a matter of easily figuring out what is Dr. Surya's answer, because I know the average of all the people. I know everybody else's answer. Let's say I'm truly an adversary. I have somehow bribed everybody else and gotten their answers. I could not just bribe Dr. Surya, but now because I know the average, I can figure out what her answer is. So now you trust me, but then you don't trust the world outside. So which means, now is there a different way we can release something to the world without you giving me noisy answers? One way is you give me noisy answers, which means that it's as good as you don't trust me, and then I compute the average and give it out to the world. That is private, right? So because you have anyway not trusted me also, you think I am as good as the outer world, so you did not trust me, you gave me a noisy answer, I computed a noisy average, gave it to the world, and then that's private, that has certain utility which we saw now. Now, because now I am trustworthy, you can afford to give me the true answer. But now the world is not trustworthy. So what we can do is, we can not, by each one of you not adding noise or giving me a noisy response, then the burden of adding noise now gets shifted to me. Which means what I will do is, in this trusted curator model, the curator will receive all the true information, compute the average, and now instead of giving the average to the world, I'm going to add some noise to this average and give it to the world. Right? So now each one of you is not adding noise. Each one of you is giving me the truth. And me, I am adding the noise and giving it to the world. And it so happens that if you do it this way, you will still be able to preserve privacy, but the utility will go up by a big factor. Right? So which means that for the same level of privacy, you will get better utility guarantees. And we'll talk about this in a minute now, right? So this method is as follows. So in a machine learning context, let's talk a bit about machine learning. I have data, and now I have an algorithm, and now I compute a model, and then I want to release this model. But what I don't release is the model, but what I will actually release is, I will release model plus noise. That's what I'm going to release. right? So now this noise will make sure that, you know, if somebody receives this model plus noise, they will not be able to figure out anything about the data. Even if they know everything except one data point, they will still not be able to figure out whether that data point's information was certain value or not. Yeah. So that's the method that we are going to see, right? So we'll do the machine learning thing in a bit, but let's try to apply the same thing to our problem here, right? So our problem was, you know, computing average, right? So now how much noise should I add to the average, right? So I have x1 to xn, and then my algorithm in this simple voting thing is going to compute 1 by n sum over I equal to 1 to n xi. It's just going to compute the average, right? So that's the average. Now I want to add some noise to this average and release it to the outer world. So how much noise should I add? Well, that depends on, you know, how much does this average change if one person changes their data. In other words, this is what is called as the sensitivity of the data. So what is the sensitivity? Well, the sensitivity is, let's say there are 100 people, 99 people's data remained the same, only one person's data changed, right? So which means, you know, if there are n people, so initially it would have been 1 by n sum over n xi. This is the average. Now, you know, this value is same as, you know, 1 by n sum over I equals 1 to n minus 1 xi plus x. This is the nth guy, right? So now if the nth guy's value changes, right? So from xn, if xn was 1, you know, it becomes 0. If xn was 0, it becomes 1, right? So then how much does the average change, right? So the average will become 1 by n sum over I equals n minus 1 xi plus, what does this become? Well, this becomes, let's say, xn prime, where xn prime is just the flipped version of xn. If this guy's value was 1, if this guy voted, now in this, you know, if I change that person's value from 1 to 0, how much does the average change? That's what I'm asking. How much can the average change, right? So what will it be now? Which means that this will be 1 by n initially sum over I equals 1 to n xn minus this new values 1 by n sum over I equals 1 to n xn prime. But xn prime and xn are almost the same, except the last guy is different. So this is 1 by n sum over I equals 1 n minus 1 xn plus 1 by n xn minus 1 by n sum over I equals 1 to n xn, because the first n minus 1, because the first n minus 1 guys are the same, plus 1 by n xn prime. The last guy only changes, so now I can cancel out this term and this term. So what remains is 1 by n xn minus 1 by n xn prime, which is just 1 by n xn minus xn prime. But what is xn minus xn prime? What is that value?
That is 1.
Yeah, very good. Why is it 1?
Because either it may be 1 minus 0 or 0 minus 1. That is flipped value, right?
Flipped value. So this is 1, right? So which means this is 1 by n. So basically what then we are saying is, if one person's value changes, the average can change at max by 1 by n. In fact, it exactly changes by 1 by n, right? So which means that, you know, if there are two data sets with just one person's value changing, then what we are trying to compute from this data set, our algorithm is computing the average, and the average can change only by 1 by n, which means, you know, if I have to confuse somebody by adding noise, the amount of noise that I should add should depend on how much can this average change, right? So if the average changes very, very less, right? So then I kind of have to add a lot of noise to confuse. But if the average changes a lot, then I don't have to add a lot of noises, because so maybe I'm doing the other way, right? So if the so basically what I'm saying is, if the sensitivity is large, so let me think about this. So if the if by changing one entry, if the output does not change by a lot, then I don't have to add a lot of noise. Yeah, that's the right way to say it. Right? So I don't have to add a lot of noise. But if the output changes by a lot, let's say if the output was 10, and now if one person's data changed and the output suddenly became 100, right? So the truth was initially 10, one person's data changed and the truth suddenly became 100 by just changing one person. Now, I have to give an answer, and that by looking at that answer, I should not be able to say whether it came from 10 or whether it came from 100, which means that I should add a lot of noise to confuse between 10 and 100. On the other hand, if the output was 10, but then if I change 1%, it just became 11. Now to confuse between 10 and 11, I don't have to add a lot of noise. I can add a smaller amount of noise. Which means if the output is really sensitive, right? So it means if the output changes by a lot by changing one person's input, then I have to add a lot of noise to confuse the final, the adversary. But if the output does not change by much, then I have to add a small amount of noise to confuse the adversary, because the output is kind of stable. So the amount of noise that I should add, right? So the noise should depend on sensitivity. So how exactly does it depend on sensitivity? Well, the method which I want to talk about is what is called as an epsilon differential privacy, which suggests the following. It tells us, well, you add the noise, which is what is called as Laplace distributed noise. That depends on sensitivity. And how exactly, I'll tell you now. What is Laplace distribution? Well, I'm sure all of you must have heard about the Gaussian distribution, right? So, or the normal distribution, right? So how does the PDF of a probability density function of a Gaussian distribution look like? Can somebody tell me that?
Bell shape.
Very good. It looks like this, right? So it looks like a bell shape. Yeah. Now, so anybody knows the function of this, right? So if this is x and this is f of x, the bell shape's function, does anybody remember the function? That's okay. So this is basically e power minus x minus mu square by 2 sigma squared by 1 by square root 2 pi sigma, right? So that's this function, but it has a bell shape. Now this is the Gaussian distribution that all of us are familiar with. The Laplace distribution, which is very special for privacy, is very similar to this, right? So it looks like this. The density looks not like bell, it looks a little sharper, that's all. It will look like this. Yeah. So the formula for this will be something like f of x is some 1 by 2b e power minus x minus mu by b. Right, so like how mean and variance determine the Gaussian density, right? So this is the mean, this is the variance that determines this bell shape. Here, the two values that determine the bell shape are mu and b. Yeah, b can be thought of as like variance. Now, what then? This is the mean. This is a mean. If it is mean 0, then this is 1 by 2b e power minus absolute value of x by b. This b can be thought of as like the variance. So now what is the suggestion? The suggestion is, release, compute the average, compute average, which is, I get all your values 1 by n. Each one of you gives me 0 or 1. I get all the values. I compute the average, but I don't give the average to the world. I release average plus noise, and I'm going to call this noise as eta. And this noise is distributed Laplace with 0 mean and variance that depends on two things. One is the sensitivity, and the other is the amount of privacy that I want. Yeah. So this is the sensitivity. and this is privacy. So this is a very interesting way to add noise, right? So what this is telling me is, if the sensitivity is small, what does that mean? That means that if I change one person's input, the output does not change by large, right? So if the sensitivity is small, one person does not have too much effect on the output. Then that means that what the noise that we are adding, the variance of that noise, you can think of this term as roughly like the variance. The variance of the noise is small. If the variance of the noise is small, then that means that you had some true value. Let's say your true value was some 25.5, right? So let's say I got all the numbers from this, I computed the average, that average turned out to be 25.5. I'm not releasing the truth as 25.5, but then what I'm releasing is, I'm releasing 25.5 plus some noise, which means that, what I'm releasing is going to have a distribution like this. It's going to have the highest chance of being close to 25.5, but then there is some variance to it. Now that variance depends on, sorry, can somebody?
Is there any doubts?
No, I think some. Yeah. So if the sensitivity is small, then what I'm adding is a small amount of variance noise. On the other hand, if the sensitivity is large, for the same value that I compute, if somehow the average had a larger sensitivity, then I will still be, my average will be 25.5, and now I'm going to add noise, but this noise will have a much more sensitivity. Sorry, again, carefully. Which means that if I now draw a sample from this distribution, maybe it will be somewhere here, right? So maybe instead of 25.5, I might say 26.3. Whereas if the sensitivity is large, then the variance becomes large, which means that I'm going to add a larger noise. If I add a larger noise and I sample something from this, maybe I'll get some value which is 38.3 or something like that, right? So because I need to add this noise to confuse you whether it was, a data set with 1 for a particular person or a data set with 0 for that particular person. Yeah. So that's the basic idea, right? So the variance of the noise depends on how sensitive is your data in determining the output. So is that idea clear? Any questions there? Okay. So now one can argue that this preserves privacy and this also has some good utility. I won't really discuss much about that. We can argue that this also has privacy, epsilon differential privacy, and this also has some utility guarantees which look like 1 by epsilon times n, right? So the same kind of a utility guarantee, which means but a better dependence on n. Let's not worry about the exact details for that at the moment. But the main idea is very simple. You compute the average and add noise. And now the same idea works for machine learning models also. That's what is called as differential privacy. So this noise that you add will depend on, let's say if you take your favorite machine learning algorithm, let's say logistic regression or support vector machine, whatever that algorithm is, right? So k nearest, whichever algorithm that you are aware of. Now, if I change the data, right? So if I take one data point away and then put one other data point, so I'm sure all of you understand support vector machines or at least heard of that term.
Yes, sir. Yes, sir.
Yeah, good. Okay. So if I think of support vector machine as an algorithm, right? So then what then I'm saying is, let's say I had some data points like this, these are green class, and let's say there is some red class data points. And now I train the support vector machine algorithm, I get some W direction like this, right? So which means that this is my W star. And then in this, if the data point falls on this side, I'm going to say +1, red, and if it falls on the other side, I'm going to say it is green, right? Now, what is the sensitivity of the support vector machine algorithm itself? Well, I can take any point, let's say I remove this point and then replace it with a different point. Maybe I replace it with a different point here. yeah, maybe any point. You can take any point and replace it with any other point. Now I'm asking, how does that W change, right? So how does my model change? Maybe my model got flipped from here to here, right? So maybe this is W dash. Now this is the sensitivity of the model itself. Now, whether this person's value was this green point or this red point will determine whether I got W star as output or W prime as output. Now I want to confuse the adversary whether it is W star or W prime, which means that I want to add noise which is proportional to how much is this difference between W star and W prime, right? So that is the sensitivity, and I will now add a noise, and then what I will release is, whatever I compute W star plus some noise, right? So now you are going to use, so now the question is, the adversary, because this is a noisy model that I'm releasing, the adversary will not be able to figure out whether a particular data point was in a particular class or not, and things like that. The adversary will not be able to figure out anything about specific questions about a data point. Now we can ask, well, how good is this model, right? So I want to make predictions about this model. I mean, for new emails, let's say I'm going to use this W to make predictions for new emails. Now, if the sensitivity is not too much, then your W has, even the noisy version of the W has not shifted too much, which means that earlier maybe you are using this line to separate the positives from the negatives for prediction. Now you might have a noisy version of it, and maybe you use this line to make that separation. So which means that the only place where you will find difference is in this region, right? So this is the only region where earlier the green would have said positive, but then now the red line is saying negative. It's left to the red line, but then right to the green line. And in this region, it's left to the green line and right to the red line. This is a small region of space where I'm going to predict incorrectly with respect to the truth. But that's okay, right? So I mean, the chance that your test data is going to fall in the small space is going to be lesser, hopefully. And so the noisy version of the model that you release is still useful to make predictions, right? So that's the idea. But what you've gained is privacy, in the sense that an adversary will not be able to figure out whether you had a particular disease or not, right? So of course you might lose out a little bit on the accuracy because of the noise that got added to the model, but that's okay, right? So a little bit of accuracy loss is still manageable as long as you can guarantee privacy. There's always going to be some trade-off. In a differential privacy sense, it's going to be privacy accuracy trade-off, right? So in the survey example that we saw earlier, it's privacy utility trade-off, right? So, but then now we have a very nice method to add this noise using Laplace distribution and so on, so that we can control the trade-off in a very statistically, robust way. So there are different, variations of this technique, but the basic idea is, you have to add careful noise. If you have to take away one simple thing from this whole presentation, the way to preserve privacy in a statistical sense is by adding careful noise, right? So you don't give the model as such, but then you give a noisy version of the model. But how you add noise is very, very important, and that's why we need to study, these methods and so on. This particular method is called epsilon differential privacy. This was in fact proposed by somebody called Cynthia Dwork, who is a leading researcher in machine learning, and this was proposed by folks at Microsoft Research along with Cynthia. I think this was proposed by Cynthia Dwork, and then a lot of people in Microsoft Research also later on worked on this problem, and other researchers as well, right? So and I'm bringing this up a point about Microsoft Research because to say that this is a very, very industry oriented ideas that have emerged. It's not just for theoretical interest. It's not just for academic purposes, but then this is actually being used in an industrial setup as well, especially in healthcare and other places. So let me pause here. I think I've taken 1.5 hours for this talk. So let me pause here. So this is the broader idea that I wanted to give. If there are any questions or any thoughts, I mean, we can take that and then we can finish. Yeah.
So sorry for interrupting.
Yeah.
The session was actually planned for 1.5 hours.
Yeah.
And it seems that all the people who are
एक मिनट थोड़ा धीरे धीरे आवाज थोड़ा धीरे
these also faculties who have to come back to the job by tomorrow morning. So I'm
Okay.
extremely sorry for interrupting you, sir.
Yeah. I'm done, right? So I took 1.5 hours, but I'm done. So if there are
Yeah, it was seriously too good that people were concentrating too much on it, but still everybody has to turn back to their job by tomorrow morning.
I understand.
So I'm sorry for it, sir.
Not at all, not at all. So we can close the session here.
Yeah. I'll formally thank you, and probably after that we can close it out.
Yes.
So I take this opportunity to express my sincere gratitude for the enlightening session, explaining all high technical contents in the simplest way, sir. And probably it was totally interactive. Everywhere you were asking questions, and people are also enthusiastically answering in spite of the time being getting extended. And thanks for the active participation, and thanks for all the sincere efforts that you have taken, sir. Thank you for generously sharing your time and knowledge with us, because normally FDPs will be happening only during the morning sessions, and this is the first time it is happening during the evening sessions. So your session was the highlight of the program, and we are truly grateful for the opportunity to learn from you and even from future, sir. Thank you so much.
Thank you, madam. Thanks everybody for. I know it's too late in the night, but thank you very much, and I hope you all enjoyed. Hopefully, we'll see you at a different point in time. Thank you.
Thank you, sir. Thank you.